Thank you very much. It's great to see a full room for a science lecture here in Fairbanks. From spying on scorpions with a black light to studying two-ton elephant seals with sleep apnea, Marc Castellini has always been interested in how animals adapt to their environment. So it's appropriate tonight that he's giving a lecture entitled On Thin Ice, Marine Mammals Challenged by Climate Change. And Mike knows a lot about ice as well. He's been to the ice in Antarctica since 1977. He's been there 13 times and has spent over 3.5 years on the ice in Antarctica. And once he actually spent an entire calendar year from January through December there. I learned that he has also had 5 workman's compensation claims. There might be another one for an ear problem as we go through the evening. And 5 workman's compensation claims from working with Waddell seals. And he's also had 3 knee surgeries from working in the ice in Antarctica. So he's a real veteran of Antarctic research. And he's one of the world's preeminent experts on Waddell seals. Mike's had many contributions to Antarctic marine science, and those have been recognized by naming a part of Antarctica after him. The Castellini Bluff is a 1,500-meter high bluff on White Island in the Ross Archipelago, which was named after Mike to honor him for the work that he's done in the Antarctic. You might ask Mike what brought him to Alaska in 1989, and someone did that recently, and I'd like to read you the answer because it's kind of interesting. He jokes that he came up here on the research vessel Alpha Helix, which was the research vessel the university operated until the year before last. I was doing work in Santa Cruz on elephant seals and how they sleep. I learned that Bob Elsner was retiring from UAF. I applied and thought I had no chance. I interviewed in late September in Fairbanks. It was a gorgeous day. We were at a faculty party and the discussion was about what was going to get to the garden first, the moose or the frost. I decided this was the place I wanted to live. So Mike went back to the Antarctic after interviewing, and he actually received a job offer that was brought in by Snowmobile. And the job offer was from Vera Alexander, the former dean of the School of Fisheries and Ocean Sciences. He says the fax was barely legible and was filled with stop every now and then in it, and it's a document he still holds today. Mike has published over 70 papers and 14 book chapters. He's received a UAF Student Mentor Award, and he served as the director of the Alaska Sea Life Center in Seward. He's also served as a faculty member and director of the Institute of Marine Science at the University of Alaska Fairbanks. And he currently serves as the Associate Dean of the School of Fisheries and Ocean Sciences, where he looks after our academic programs, works on development of new programs, and does everything he can to take care of the students we have in our program. So please join me in welcoming Dr. Michael Castellini.
Okay, let's make sure you can hear me and we'll actually get this going. You're going to be on an adventure with me tonight because we put this on a new computer. We are making the assumption that all the audio and the video is going to work okay. If we have a few glitches in that during the evening, please put up with me as we work our way along. I have several tasks for you tonight to think about as we work through the talk. And that is that not only are we going to be talking about marine mammals and, for example, seals and whales and a variety of animals that live out on the ice, but I'm going to be asking you to think about the whole Earth system. And the reason I want to do about that is talk about how important the poles are to climate change, how important they are to the animals that live there, and as you all know, because we live here, how important it is to the people that live in the Arctic. And we're going to look at that by thinking in several different points of view about the Earth as a whole system. And think about it as a globe. We have a North Pole, a South Pole. Both of those poles are extremely important to the entire biology, to the climate, to the weather of the whole planet. And so what happens at the poles, what I hope to convince you tonight, is important to what happens to you here, and especially important to the animals that live there. I have the easy job. It's very easy to say we have animals that live on ice. If the ice changes, the animals have to change. We could do that lecture in 2 minutes and we'd be done. You could all go home. It wouldn't be very much fun, though, and I want to explain a little bit more about that tonight as to what those relationships are and tell you how we've actually come to some of those conclusions. I also want to do a little bit of advertisements for the whole concept of the International Polar Year and what's involved in those programs. It's thousands of scientists traveling to both the North Pole and the South Pole for about a year now and another year coming up, looking at how the relationships of the poles, like I said, impact the weather, impact the climate, impact the animals and the people that live especially in the north. And as part of that program, the National Science Foundation and NASA, a variety of other agencies are involved in it. As you know, here in Alaska and the university, we're heavily involved in International Polar Year. And one component of that is something that I call, or that has been called by the National Science Foundation, the PolarPalooza. It's a program that I'm involved in. It's a nationwide public relations program where we go from schools and universities and museums across the country talking to everybody about how important the poles are to the whole planet. And so what I'm going to do tonight is take a little bit of that PolarPalooza footage that we've used across the country so far, weave that into my story about the marine mammals, because in this program on PolarPalooza, I really only get to talk about 10 minutes or so to talk about what I'm going to spend about 30 or 40 minutes with you this evening. The good news, though, is that the PolarPalooza is coming to Alaska in May, and I'll show you a little bit of advertisement for that, and you'll get to see the whole show then, as we have it in both Anchorage and Fairbanks, talking about the International Polar Year and all the science associated with it. I don't need to remind you living here in Alaska that we can look at the Earth from the northern pole like this and see the Arctic ice there with surrounded by all the land. And it's the first thing I want to remind you is that the Arctic is primarily an ocean surrounded by land. And we're going to contrast that with the South Pole in just a second. So as you look at this image, and we've got Alaska over there on the left, you can sort of guess this is the summer image of what the ice looks like when it retreats. We'll spend quite a bit of time tonight talking about how the ice moves back and forth in the north, but the most important part is to remember that it shrinks and expands seasonally. The other thing that I want you to remember as we work throughout the evening here telling stories about the north and the south is that the Earth has changed for billions of years. It gets hot, it gets cold. I'm going to show you data for the last million years of how that temperature has gone up and down and up and down and up and down. So change has been happening, and it's going to continue to happen. What is occurring now, though, is that humans have started to impact the way in which the Earth changes. And I'll show you that from some of the greenhouse gases and the CO2 and what that's done with temperature. We'll explore that in a little while, but just keep that in the back of your mind. The Earth has always changed. It's going to continue to change, but now there are enough humans on the planet altering the way the planet actually changes, and that impacts the animals and the systems. So remember, in the north, we're going to be talking about an ocean surrounded by land, and that's going to be very critical when we talk about all the people that live there. Contrast that with the south now. Now, the South Pole is sort of the image of the opposite of that, not only from the north and south, but now we have the land, the Antarctic continent, surrounded by an ocean. So it's sort of the inverse of the north, and nobody lives in the south. We don't have indigenous peoples there. You don't have anybody that actually lives on the continent. No animals live on the continent. There are no polar bears in the south, for example. But instead, you have this large ocean around it. So the marine life that's there, the marine mammals that are there, unlike the north, where they could go all the way to the North Pole, here clearly no animals are going to go to the South Pole station itself. It's thousands of miles away from the ocean. And it's a very high, dry continent. In fact, at the South Pole Research Station, it's about 10,000 feet of ice before you reach the ground down below. The only thing that lives there are charismatic microfauna that like to live in the ice there, not much else. So most of the story in the south surrounds in the ocean around it. So remember those compare and contrast. I'll show you one last image of that from the views of a map. There on the left, again, the image you're all very familiar with here, the Arctic Ocean, surrounded by the 60-degree mark there of what is considered to be the Arctic. Many, many people live here. You all know that. We all do, and a lot of people live a lot farther north than we do here in Fairbanks. Consequently, the ice and the ocean, the marine mammals, how they interact are very important to the people that live in the north. Contrast that again to the south. There are no people that live in the south. So you've got social issues in the north associated with climate change, with marine mammals, where marine mammals are hunted, tourism issues, etc. You do not have that in the South. The South, in fact, is held by UN treaty to be an area where nobody can live. There can be no military operations there, no mining or things along those lines inside the Antarctic. So remember that throughout the evening. Ocean in the north, continent in the south. And let's explore this here a little bit as we work through what this implies. Right away, I always put this in to remind everybody, we do not have penguins up here, you know that, but we do have them in the south. Same thing, I like to tell the story, and we'll look at some pictures here of polar bears. Of course, we have polar bears in the north, not in the south. If we had polar bears in the south, I'm pretty sure we wouldn't have penguins in the south. They'd probably eat them all up. Some of the animals we'll be talking about today, and there are some people here in the audience that have worked with many of these species. We have in the north the seals. These are the true seals. They're sort of like slugs as they crawl around on the ice. And the walrus, of course, which can move around a lot faster. You have bearded seals, the beautiful ribbon seal there in the center, ringed seals, spotted seals. These are all the groups of animals that do well on the ice. The official word for that is they're pagophilic. It means they love the ice, okay? But these animals are very, very closely associated with the ice. It's where they give birth to their pups. It's where the animals rest. And so again, you could do a very simple relationship. Instead of the ice changes, then these animals have to change. In its simplest form, that would be the way to look at it, but we'll explore it more throughout the evening. In the south, we also have animals that are closely associated with the ice. You've all heard about the big leopard seals down here on the bottom. Very religious experience to be chased around in the ice by a leopard seal, I can tell you that right away. On the top left there is the Weddell seals, the animals that I've spent a great deal of time working with and living near their colonies. You'll see some video of that. And the animal on the top right, very unusual animal called a Ross seal. Very few of them have ever actually been seen. I've had the opportunity to work with 30 or 40 of them. Strange little animals, barely have a head, little teeny tiny teeth because they eat only squid instead of big teeth like this leopard seal does, who eats basically anything that comes near him. You come up to a leopard seal and it's sort of like they think lunch is delivered when you come walking up to them. So this is a little bit of an advertisement for PolarPalooza. We've been all over the country in many of these different places. This is just the 2008 schedule. I can't go to all these sites because I do have to do some work for the dean during the year. But I will be able to go to a couple of them in New York and in Washington, D.C. coming up. But I wanted you to notice up there that we will be here in Anchorage and in Fairbanks in May. Please put it on your calendar. It's great fun. It's the most entertaining public outreach I've ever done. Audio, video, different people talking about ice cores. We have people that are Alaska elders that come in and talk about what it's like to live with climate change. It's fantastic. It's really fun. We'll probably do it something like in the Herring Auditorium along those lines. It's at West Valley? Okay, thank you. I didn't know where we had done the negotiations on that yet. So I'm going to, if we got it here, give you a little bit of an opening video from Passport to Knowledge, which are the people that have organized the PolarPalooza. Many of you that are old enough here to remember Carl Sagan's Cosmos program, the same writer-producers for that have produced this show. So they're very good at what they do, and they're very good with public relations. Let me just do this now. This is the first audio and video combination. We have both. I'll try to get the audio down right since we didn't have a chance to test it. Let's make sure this actually works. Come on, babe. I'll watch the sound on here. Okay. Okay. There's our first test. There we go. Got it. Pretty amazing images of what this is like to work in the north and the south. The whole concept of PolarPalooza exactly is stories of a changing planet, so that we do tell stories of what's happening in the north and the south and relate that, like I said, to the International Polar Year and the science associated with it. And hang on here a second. Okay, so the International Polar Year, again, we want to explore tonight why the poles are important to climate change and what is the role specifically tonight of sea ice for animals and humans. Again, the South Pole here on the left, you've got the continent surrounded by the ice on the outside, and on the other hand, in the north, you've got the ice surrounded by land on the outside of it. The simplest way to think about it is if a marine mammal, a seal or something, seals cannot give birth in the water. And so when they have to have their pups, they're going to come out on land. If they're in a more temperate region, they'll come out on the ice if they're in the northern regions. During that time that they've had the pup on the ice, they have to be able to keep it warm, they have to nurse it for a few weeks, and protect it from the environment, protect it from the cold as best as possible, because seal pups, when they're first born, are terrible swimmers. They're not very good divers, they don't know how to hunt, they don't know how to get food. Their job for the first 5 or 6 weeks while they're alive is to basically get fat from mom while they nurse. And it's tremendous. You'll see pictures of this. Pups are born, in some cases, at about 25 pounds, and 6 weeks later, for those of you that have nursed your own kids, they weigh 125 pounds. And you'll see us trying to pick them up and weigh them. So their job is to stay out on the ice and become a very fat seal pup, or a wiener as we call them, and that's very hard to do if the sea ice goes away. So that is the most and primary relationship to it, and like I said, we'll look at that from a couple different directions. Okay, let's look at this now. Everybody talks about the ice changing. I've already told you the planet's changing. It's been changing for billions of years. Let's look to see what's happened in about the last 25 years for ice here in the Arctic and the Arctic Ocean. What you're going to be seeing here now is a plot of how much the ice has shrunk during the summer. I have people come up to me and ask me all the time, oh, I hear in 20 years there's going to be no more ice in the Arctic Ocean. That's not true. There's always going to be ice in the Arctic, especially in the wintertime. What they're looking at now, though, is how much it shrinks during the summer. So let's watch this video here for a second, and I'll tell you how this is supposed to work. Here we go. Okay, so what we're doing is we're zooming up here looking at the annual sea ice minimum. You can see it expanding and contracting every year. And it's being plotted here since 1979. You can sort of see a slow drift down and how it's drifting down during the summer. In 2005, hit an extremely low level and then crashed in 2007. The projections, as those of you read in the Anchorage Daily News and everything from this last week, projections for 2008 are to be less than 2007. And so the models that we had applied from 1990 to about 2000, those were the ones that you heard where people said, well, maybe we'll have an ice-free summer in the Arctic, maybe about 2030 or 2050. The projections now, given what's happened in the last 5 years of 2007 and now the projection for 2008, is the ice-free time will probably be around 2015 or so not that long from now. A whole bunch of geopolitical implications of that in terms of opening up the Northwest Passage, oil shipment, land rights. You already know Canada, Russia, the United States, everybody's up there right now trying to figure out, up here right now, trying to figure out, how shipping is going to go through there, who owns what land. But put the geopolitical aspects of that aside for a moment and just think about the animals that have to live there during the summer, that have to have their pups there or rest out on the ice. What do you do when there is no more ice? Or what do you do as that ice shrinks back so far that it moves away from where your normal hunting or feeding grounds are? I'll also tell you in terms of the humans, which we haven't talked about yet, that the human population around the Arctic, remember where all the people live north of that 60-degree mark, they've converged over thousands of years in most of these villages where the ice, the marine mammals, and the people have all come together to live at the same spot. That's why those villages are there for the most part. The ice moves away, now what do you do? Because with the ice moving away moves the marine mammals, and then how do the people make their living off the marine mammals that they need to do that? It's a real consideration, and from the social aspects of the International Polar Year and everything associated with that becomes a major consideration. Okay, again, as we look to the south, I'll talk about penguins for just a second. We have no penguins in the north. We have birds that fill the same ecological niche. But these birds are also extremely dependent on the ice, especially the ones here on the left, the big emperor penguins. The ones on the right there, the king penguins, live more like in the sub-Antarctic regions. We're out here diving with these birds at the moment. Tremendous birds, incredible ability to dive. This species here we now know can go to just under 2,000 feet deep while they're down there hunting. And pretty impressive birds and animals to be with it. I'll have some video for you in a moment, in fact coming up right now, of penguins as the first animal species that we can explore tonight in terms of working on the ice. Okay, so now what we did here, this is a group from Penguin Science that produced this for PolarPalooza. It's a really good trick. Penguins are incredibly curious animals. So what they did here is they took a video camera, went and dug a little ditch, put it right in the middle of a penguin rookery, and turned on the video camera and let the birds come up and explore it. So you'll get to see this now as to how these animals react to the camera. I'll see if I got the audio right now because they make some noise and I don't want to sort of blow yours out. There we go. That's just about the right sound. These birds are exquisitely adapted to the ice. See the big claws on the toes? That's so they can move around and on the ice like that very easily without slipping and falling. These are Adelie penguins. They're about this big. These are the comic penguins that everybody always shows in TVs and shows and stuff. They'll always stay about one wing beat away from one another. You'll see as they come up and they sort of whap at each other with the wings. Incredible thermoregulation capabilities, the ability to hold their temperature under these cold conditions. They can flush and become very blushed underneath the wings if they need to get rid of heat. They can have a whole bunch of other tricks to do that, but you'll see one of the things, they keep their feathers, for example, almost all the way down to the bottom of their feet. Those of you that have seen the March of the Penguins and saw the large emperors, you know that these birds live under extremely rigorous conditions out on the sea ice, and for them, changes in the sea ice are critical, because that's where they go to molt. They go out and sit on the ice to molt. They can't do that in the water. They've got to stay out of the water in order to be able to do that, and in many cases, as you saw with the emperor penguins, they also need the ability to raise their chicks under those conditions. Okay, now when I talk about the north, everybody immediately goes Nanook, polar bears. So let's see what we're talking about here with this species. Wonderful footage again. This is from courtesy of the Cornell Ornithology Lab. This is of a polar bear hunting on the northern ice. Exquisitely adapted to the ice. You've all seen them at the airport with their, the stuffed animals. Many of you have probably seen live polar bears. Fur on the bottom of the feet so they can walk around, not only stay warm, but be very, very quiet. This animal is out hunting on the sea ice right now for ring seals. Ring seals are its primary prey, and the ring seals are hiding underneath the ice and the snow or underneath the little snow caves, and she is trying to bash her way into the snow cave so she can get down to the ring seals, which she needs to eat because she needs to give it to these cubs. These animals are predators. They're the largest predator on the planet at the moment. She weighs probably about 900 pounds, and they eat seal primarily. They need the ice to rest. They need the ice to raise their cubs. They need the ice to get out of the water. They can't stay in the water forever. And you've all read the stories. I don't need to keep telling you of various stories coming in about, well, polar bears, there's no more ice. They're starting to, some of them are drown, etc. However, watch how beautiful they are in the water. It's an 800-pound animal. No belly flop here. Look at this. That's great. This animal is very adapted to be in the water. They're good divers. They're good swimmers. We now have some evidence that they're actually eating fish also. And what she's swimming with here are beluga whales. They're in the background. All of these animals live in the Arctic where the ice and the air and the land interface with one another so that the polar bear can come onto land when it needs to. And now people that work on the islands in the north are telling us that more and more bears are coming onto land because they need to eat, and they're starting to move into bird rookeries, for example, and starting to eat birds because they can't get access to the ice and to the seals that they need. As I mentioned before, ice also directly impacts humans' access to marine mammals, whether we're hunting whale in both of these cases or whether they're hunting seals. The people that live in the north that depend so much on their marine diet, it's critical to them where that ice comes in. I've been in Barrow while they've been hunting whales. I'll show you pictures of that later tonight. And the last time I was there, which was maybe about 3 or 4 years ago now when they were hunting, the ice was so far out, 30 miles out, and they're going out in tiny boats, that the elders are going, this is really bad. We don't want our people 30 miles out to sea trying to whale. This is not a good place to be. We need the ice to come closer in so that the whales come closer in so that we're not as much of a risk. Now translate that into minimal ice hundreds of miles away from the coastline, and you can see where the social impacts of this come in. Okay, Barrow, lots of you have probably been to Barrow, very, very dependent upon the ice and what happens to it every year. An interesting story about the people in Barrow is they'll tell you that we've adapted for thousands of years. The ice may go, the ice may come, it might get warm, it might make cold. We will move our way through this and figure it out. The problem is, though, what do you do about all the infrastructure that's necessary to keep the village of Barrow or all the other villages going? You can come up with some, quick answer off the top of your head and say, well, the infrastructure is important, it's important to the people, but there are hospitals and schools and everything else associated with these villages. If the infrastructure has to change because the coastline changes, or as we know out on the west coast, you're talking about moving entire villages as climate change occurs, it becomes much more serious than just saying, well, we'll figure out how to adapt to it. It becomes a major social issue, and again, that's one of the themes of IPY, especially here at the University of Alaska in Fairbanks, as we look at the social and economic and political implications of change. So let's explore here a little bit then how we actually work with seals out on the ice and why I've come to some of the conclusions why ice is so important to them. These are, in this particular case, Weddell seals out on the sea ice in the Antarctic next to an active volcano, actually Mount Erebus. And you begin to wonder, well, okay, why is the ice changing? Everybody talks about CO2, everybody talks about climate change. What are actually what's some of the information that we want to see here? What I've plotted out for you here now is carbon dioxide concentration in the Earth's atmosphere for the last 350,000 years. You can see it come up very fast for about 10,000 years and slow and go down for about 90,000, up, down, back and forth. What I want you to notice, because we'll come back to it in just a few minutes, is the peak levels for about the last, 300,000, we could take the data back about 1 million years, is somewhere in the range of around 280 to 290 parts per million, about a little bit less than 0.03%, if you think about it in those terms. Now let's consider what temperature has done. And if you'll notice, those two things look an awful lot similar to one another, so I'm going to overlay them here for you. Temperature and CO2 track one another. They've tracked one another for the last 1 million years. That cycle, the up for 10,000, down for 90, is due to a solar cycle, the way that the Earth relates to the sun in terms of its orbit. And those cycles move through. There's 20,000-year cycles, 40,000-year cycles, but the main take-home message here is CO2 and temperature trace one another. The way we get this information is really cool. Mainly you get this from ice cores that can be taken out from the Antarctic. In fact, that's where these data come from. They can drill out ice cores that are 1 million years old from ice that's 10,000 feet thick, remember, and go backwards in time and measure the CO2, and with some really interesting chemistry, be able to tell you what the temperature was also. So now we've tracked it, but now let's go over here, and I'm going to expand the last 150 years for you here in a second. We've had peak CO2 concentrations of 280, maybe 300 there. The value today is somewhere around 385. It's getting ready to approach 400 parts per million. It's going way high in the last 150 years because we've now sort of broken into the natural CO2 cycle as humans. And as CO2 ordinarily takes millions of years to cycle around in the planet, as it comes in and out of fossil fuels and the whole system evolves and erodes, etc. Now it's, instead of slowly moving like this, we've broken into that circle and we're up here with CO2 doing this. And so we're pumping out all this CO2. Now there's only several things that can happen. If the Earth acts like it has for the last 1 million years, that's where you get the increasing temperature predictions, right? Because the two of them have tracked one another. So one scenario is to say, if this is true and the very high numbers over here continue to go high, then temperature is going to follow along with it. So far, that seems to be happening. Temperature is increasing across the planet. Is it solely due to CO2? Don't know the answer to that. But we can tell you, if you look at the evidence for the last 300,000 years, it's going to suggest it's going to happen. On the other hand, you can take the opposite side of that and say, no, you're all just making this up. The CO2 data are real. Nobody ever contests that, but maybe that's not what the temperature is going to do. Okay, let's assume that's not what the temperature is going to do. Now what are you going to do with all that CO2 instead? For the last million years, this planet has never separated CO2 and temperature from one another. Now we're going to move into a state where those two things are separated from one another, and we do not know how to model that because we've never seen it. One way or the other, we have a lot of work to do in terms of figuring out how CO2 and temperature, or just CO2, how it dissolves into the ocean, how it's going to affect like the acidity levels of the ocean. We've got to try to figure that out. And the hope is that by letting everybody know that we've got a situation here, that we've got a problem with trying to control CO2 in the planet, that there's going to be somebody, some Bill Gates of carbon dioxide, that's going to figure out how to sequester this stuff or figure out how to resolve the problems that are associated with it. So I want to explore just the last 150 years there, because it's really a very interesting pattern that's happened in the last couple hundred years. So there are the ice core records on the left. We had the ice core records on the left. All right, hang on a second. Try backing up here again in a second. Hopefully it's going to stay there. Good, okay. Ice core records there on the left. Those are the data that you were seeing. Remember, there's the 270, 290 parts per thousand up till around 1850. And then we've started the increase here. Those are the sort of the yearly cycles there on the upper little graph, so you can sort of see what it does inside a year as you go through summer and winter. But you can see right now, and this was only up to about 1999, and we peaked there at 370, and like I said, the number this year right now is about 386 parts per thousand. That's the last 150 years expanded versus that 300,000 I just showed you a minute ago. We've got to do something about this because, like I said, either the Earth's going to follow along and the temperature is going to go up, of which we have some pretty good evidence that's happening, or they're going to separate from one another, and then we have no idea what's going to happen in terms of the chemistry of the planet and how we interact with temperature and CO2 and everything else that CO2 does. One way or the other, we need to be working on this, and the way to do that is by you going home and saying, geez, you know, that maybe there's something I can do with carbon issues of maybe energy, maybe there's something I can do about letting people know this is important. But the most important thing of all is for you to understand that when we talk about the Earth as a system, that the next time somebody says to you, oh, you know, who cares if a walrus dies or something, it doesn't impact me in Louisiana. Actually, it does, because that is just a symbol of what is happening, of the fact that the planet is changing, and it's changing because we're altering it. And it doesn't matter if you live in Louisiana, it doesn't matter if you live in Barrow, climate change is going to impact us, whether that's flooding issues or whether that's climate change in terms of sea level or whether it's weather patterns and storm patterns. It impacts all of us. For, like I said, for me, it's the easy job in terms of the marine mammals that live there. So I want to show you a little bit of footage now of us working on the ice with seals. This is one of our sea ice camps that we put out on the sea ice in the Antarctic. The ice underneath our feet while we're walking around here is about 5 to 6 feet thick, and we've put our camp up near a seal rookery, a seal colony, where the seals are having their pups and raising their pups. And once again, we'll hope along with me that we can get this to go here. We'll see. No? Yes? No? Okay. Not seeing it, are we? Okay, we're going to try this again. I apologize for this. It's a problem with switching out material right at the very end. Try it one more time. I'll wait till I see if I can get it up here. If not, we'll have to skip it. Which is unfortunate because several of the faculty members that we're interviewing in Fairbanks for a new position there in marine mammal biology are actually in this video. We're not going to have it. Let's see if we can get back to the other stuff. I put in some stills just in case we couldn't get to the video on that one. I apologize for that. Here we are working out on our sea ice camp. Oh, that's not a camp. That's just still a temporary hut that we have with us. I wouldn't want to live in there for months and months. That's way too small. But what we can do is we can work out on tracked vehicles. Again, the sea ice here is about 5 or 6 feet thick. And we've been able now to come up to these seals. And here's a mother and her pup. The pup's about 3 or 4 days old. Now I want you to notice a couple things right away. These are totally wild animals. This female weighs about 900 pounds or so. Her pup probably weighs about 50 or 60 pounds at the moment. I can walk right up to her. You're going to see images of us here just walking up and picking up the pup. Now imagine one of the moose that's out here right now, you walking up to one of the calves and saying, hey, I'm going to take this calf over here and weigh it. Not going to happen. Imagine with a bear, it's not going to happen, especially with a bear, right? Why is that? I mean, why can you do this in the South? Very simple reason, nobody's ever lived there, right? They've never ever been hunted, and there are no polar bears. There are no land-based predators for these animals. I walk up to them, and I'm just a weird penguin in a black or a red outfit. I am no threat to them, and consequently, we can just walk right up to them, which makes them incredibly easy to work with. You can ask many of the people here that worked with seals in the north. That is not true in the north, because they know about polar bears, and they know about hunters. 300 yards away, they're gone. You know, bye, see ya. These guys, we just can walk right up to them. Incredibly easy to work with. So when I talk about the ice, here's a female. She's given birth on the ice. This is a rookery. There's hundreds of seals all over the place, and they're there having their pups. Here's a brand new little pup over there on the right. He's the one that weighs about 25 pounds. She's not still pregnant. She's just loaded up with fat to feed that pup for the next 6 weeks, because he's going to grow to be 125 pounds, about maybe 3 or 4 times the size of that one there with one of my students holding the pup, who still has its umbilical cord, so it's less than a week old. So we can walk right up to them, hold them like this, measure them. What are the things that we do? Well, we know, like I told you, that they're not very good divers. We've been able to figure that out. They don't actually stay warm very well if they get in the water. That fur coat there is great for staying warm out on the ice surface, totally terrible for staying warm in the water. So we can measure them, pick them up, weigh them, put them in a bag, lift them up. That's the only way you're ever going to get them to be when they're 125 pounds. And at that point is when you're wanting bigger and bigger graduate students with you, so it's easier and easier to lift. You lift about 40 or 50 of those a day and you get your exercise with these animals. But again, we then just take the pup out of the bag and put it back next to mom, and they're fine. So one of the things that we're very interested in for all these animals, north or south, is how fast does that pup grow? How soon can it go into the water? Some of it depends on how fat it gets, because it needs that blubber to stay warm. Some of it depends on how soon it sheds its fur and develops its adult fur, which will help protect it even more against some of the abrasions in the ice. But the important and critical part for all of these seals is how much blubber they can put on, how much fat they can put on. Their fur coat does essentially nothing for them in terms of staying warm in the water. The whole thing is how much blubber can you put on, how fast you can put it on as a pup. You take the ice away, you've eliminated the ability for the pup to be able to get enough blubber on it fast enough in order for it to stay warm. The fur coat is beautiful for a pup, totally useless in the water. And that's why it is so critical that the timing that they have on the ice in order to get large and fat is very important. The water's very cold in the north and the south. It's a degree or 2 below freezing. And they're warm-blooded animals, just like you or me. They need that blubber layer. So this is how seals stay warm. You'll see up here in the top left, there's a pup there that's been protected. That actually is mom there on the left of the pup. She's looking at me. I call this picture Pup and Mummy, because that's what she looks like there. She's totally covered herself in a snow blanket and has protected the pup from a blizzard. So the pup cuddled up next to the mom. The blizzard comes over, covers her with snow, and she's protected the pup. Okay, now this picture on the lower right needs an explanation. That is a seal shadow where the seal has essentially melted its way into the ice. So you can see the 2 flippers there in the back and then the core of the animal here on the left. Well, that's pretty strange. How can the animal melt its way into the ice if it can sit there with that kind of snow on it, on the surface over here on the left? Those 2 things can't happen. This animal would have to have melted all that snow first. It's because they have the incredible ability to control how much blood actually goes out to their skin and to the surface. When they need to cool down, they can flush or blush, if you want to call it that, and get the heat out to the skin. Their skin gets very warm. I've watched them steam, just steam coming off of them, and they can actually almost melt their way into the ice if they get warm. On the other hand, if she needs to stay nice and warm, then she shuts the blood flow off to the outside and she can let herself be covered with snow, and that won't melt off of her. So incredible ability to what we call thermoregulate, ability to control how much blood and heat comes out through that blubber. And again, this is a really critical organ for marine mammals. Blubber is not just fat, and it's not like your steak fat. You can go home and cook, or hamburger fat or something, and watch it sort of melt and turn into all the wonderful stuff you see in your frying pan after you've had bacon. It's not like that. Blubber is an actual organ. It's structure. It's almost like a sponge, and it's an incredible material that the animals very carefully regulate because it helps them control temperature, It helps them control buoyancy. It streamlines them a little bit so they look a lot like submarines, and seals thought of it first before the U.S. Navy did. And they also have the ability to control how much water they have by holding water in that blubber too. Very important organ for them, and it's not just fat like you'd have on your steak. And this is how humans who study seals stay warm. This is what we have to do. Bunny boots you're all familiar with. We show this picture to like kids in Texas, and they go, "What are you wearing on your feet?" Those things, are they funny boots or are they bunny boots, I think is the question that they ask us. You're familiar with them, of course. We have to wear them all the time out on the ice, and of course with the big parkas, protect yourself. The difference is between a seal and you or me when you put on your parkas 2 weeks ago when it was minus 45. You can unzip your parka, right, when you're exercising really hard. Those of you that went out skiing today or something, you probably unzipped your polar fleece a little bit because you were exercising, you were getting very warm. You have to be able to control how hot you got, right? I don't remember ever seeing zippers on blubber, on seals, or blubber that exists in the penguins. And that's why blood flow is so important to them, because they can't unzip themselves out of that blubber coat. It'd be very, very easy to design a seal to stay warm. You just cover it in blubber. Very, very hard then to cool the seal down when it's got to be able to go out and exercise and swim and chase people around on the ice or whatever it's doing, because it can't unzip that blubber coat. It has to be able to dump the heat out. I can take my boots off, I can unzip my parka, the seals can't do that. And so for them, thermoregulation is critically important, and again, that's part of the development of being a pup and why the ice is so important. Also very beautiful animals. One of my, one of my favorite shots here of southern elephant seals. These guys, actually they smell worse than they look, actually. And they're huge. These are the largest seals in the world. These guys weigh about 3,500 pounds and are big. They're longer than the screen is long, have a bad attitude, and don't smell very nice, and they lay all over the top of one another. But they are exquisite divers. Huge control of blubber on these animals. Very, very important for buoyancy, very important for diving. These animals also venture into the ice. In the south, and in the north, they'll venture into the northern ice also. In fact, the ones in California come up here off the Aleutians to feed the large males. These are large males, and again, very, very big animals, totally covered in blubber, as so much so, in fact, that before we put the Antarctic Treaty into effect, a great deal of the hunting in the south was for this species, and you can go out on beaches now in the sub-Antarctic and see them just littered with elephant seal bones, because they came in to take these animals, to take all the blubber and melt the blubber down and use that for oil. I hate to keep talking about blubber as sort of the central theme here, but if the concept is ice, the concept is staying warm, the concept is being able to put that blubber on. All these animals tend to do that. We also do lots of work with whales. He's not actually shooting the killer whale in this case. He's actually shooting a dart into the animal so he can trace it. Attached to the dart is a satellite tag. This is one of our research members here from University of Alaska Fairbanks, although he's down in Seward at the moment, Russ Andrews, who has developed tags that he can put on orca and track them all over the place. Okay, what's that have to do with ice? Well, first of all, in the south, the orca and the ice are very closely associated. Here in the north, as some of you probably know, there's a lot of questions about whether or not the orca are eating otters and whether or not they're eating stellar sea lions and eating all these animals. And they need to know where those orca are going. And Russ is one of the people that's figured out how you actually put a tag in an orca and figure that out. Again, these animals are very, very dependent upon blubber. It's very critical to them. In Barrow and in half a dozen villages across the northern Arctic, they hunt bowhead whales. So here's a bowhead whale laying on its back that they brought up onto the beach in Barrow. I want you to notice how thick that blubber is coming off this animal. And this particular animal is fairly small. It's only about 18 inches thick. That is one big coat in terms of staying warm. I'll show you another picture here, and clearly very important for food for both the people that eat the animals and for the whales themselves. It's very thick. Look at this layer up here on the top left, or as it is the people are measuring it here on the right. This material is critical to the whale for its long migrations, because it's food and fuel for it while it's migrating, but also very important for it staying warm. But the problem is for bowhead whales, the calculation goes the other way. They have too much blubber. If it was solely for staying warm, they wouldn't need nearly as much as this. In fact, they're over-insulated by a long shot. And so now we've got a problem with how you actually cool a whale down. And to do that, that's why they need that really good blood flow, because they've got really too much blubber if you were doing it just on calculations of being able to stay warm. Dennis mentioned that I'd spent the year in the Antarctic, and here I am sitting on an island, in fact, not coincidentally, on Castellini Bluff there in the background, at a sunrise occurring after 4 or 5 months of no sun. And what you're seeing up here on the left are what we call nacreous clouds or noctilucent clouds. Very, very important for the Antarctic. They form when it's very cold. It's got to be -80 or colder for these clouds to form. Why do I have them here? When those clouds form, they form the basis, sort of like the chemical structure on which the chemical reactions, you all heard of CFCs, chlorofluorocarbons, that were wiping out the ozone hole. It was occurring on the surfaces of these clouds during the springtime, which is exactly what you're seeing here with these clouds that sort of glow like mother of pearl. The reason I bring this up is the ozone hole is the poster child of how the world has dealt with a major environmental issue. We knew we had this problem. We started seeing it about 40 years ago. We realized the problem as humans, that we had to get rid of the chlorofluorocarbons in order to resolve this problem. The world's nations did that. We've removed the chlorofluorocarbons from your hairspray and everything else. The ozone hole is starting to repair itself. Exactly the same concept needs now to be applied to the way we think about the world and the way the world reacts to the concept of the greenhouse gases. We need to demonstrate what's there. Nobody argues about the CO2 data. You won't find a single person saying the CO2 data are wrong. Where the argument gets down into is where the models predict where it's going to go in terms of future issues or what's causing it or how to solve it and the politics and economics associated with it. We've done it before. We can do it again. There's no reason why we can't get a hold of this. And this is, like I said, the poster child in terms of following the same path for some of the greenhouse gases. The ice is beautiful. It's a wonderful place to work. I love working on it, even barring all the surgeries and everything associated with actually having to be on it and working with the large animals. An amazing place to see, an amazing place to be around and see the animals that are adapted to live there. That's my job. I understand how, I'm supposed to understand anyway, at least teach students how animals adapt to their environment. The class that I teach, for example, in marine science here, very, very simple outline of the class. We have to build an animal that can live in the ocean. And so we talk about all the different things necessary for an animal to live in the ocean. In this case, we're talking about animals that need to live on the ice, associated with the ice, one way or the other, in terms of hunting, fishing, resting, or everything associated with having just their normal lifestyle. So I'm going to close here with one last video, assuming that it plays, of just closing with some very nice images of both the Arctic and the Antarctic. And then I'll just summarize with one last thought after that, and then we'll go to questions and answers. I think we'll be just about on the right time for that, even given our late start. So let's get this one going here, and then I'll have you enjoy this for just a moment. There we go. And then I'll do some questions for you. And make sure I got the sound going right here too. Please show, there we go. All images from PolarPalooza. Lots of work during International Polar Year, putting people out on the ice. A lot of it funded by National Science Foundation, a lot of it funded by NASA. Coast Guard cutter Healy, we put people all over that ship. So I want to thank you for coming tonight, and I want to remind you of just one thing that we talked about at the very beginning of the evening tonight. I'd like you to leave with the idea that the Earth's a system. The poles are important. Obviously here we live close to one. But even if we were talking tonight in Texas, the poles in the north and the south are important to you. They're important to you and to your life, and what I've hoped I've shown you tonight for the animals that actually live there, the ice and how it's changing and what might change with it is vital to their life and to the people that are associated with them and to the animals themselves. I want to thank you for coming tonight. I apologize again for the audio and video problems, but I'll be happy to answer questions for you for the next little bit. Thank you very much.
Hi, Michael. Last night on the news, there was a report about the diminishing ice in the Arctic, and the suggestion was made that marine mammals would just, instead of going onto ice, would just go onto land, and that pretty much all would be well. Can you comment on that?
Yeah, the question there being, well, okay, they'll just adapt, they'll go onto land themselves. Some of them live so far away from land, this is not an issue for the ones that are in the deep polar regions. In the Antarctic, in many cases, there is no land for them to go on to, so that's a consideration as the ice goes down there. But also, in many cases, if they go onto land, then where do they hunt and find the food to feed their pups or their calves? Also not a very good option for the whales, obviously, in terms of being able to go on land, but if they need to be associated with the ice for protection or the ice for movement patterns or something. But this is the concept that, oh, everything's fine, we'll just adapt, and all the animals will be taken care of. The Earth's changed for billions of years. That was the point I was trying to make to you. Yes, the Earth has changed, it's going to continue to change, but now we're altering the system. These animals will have never faced that particular scenario before. Again, so for many of them, this is just simply not an option, and they're already starting to see that. I believe this last year with walrus going onto land, and then there were all sorts of problems associated with them being too crowded in some of these areas and actually stampeding one another. There's no doubt it's an option for many of them, but for some, it's not an option at all.
Any more questions out there?
There's one over here.
There's one up here.
Would you comment on the polar bears in Churchill, Manitoba, which I guess they're quite a bit on land. How is the rising temperature affecting them?
What he's referring to here is in the whole Churchill area, there's a population of bears in the Hudson Bay area that come on land at a variety of times during their breeding cycle. And in fact, I believe it's there that at Halloween the kids have to go out with armed guards because they're polar bears wandering the streets. In many cases, the polar bears, and they see this in Barrow also, some of their behavior is impacted by the human patterns that are there, the human habits that are there in terms of trash, access to leftover in the north. It's whale meat, things like that on the beach. And in Churchill, it's areas of them coming onto land also associated with humans. So from some aspect of that, we've already been tied in with the bears and how that behavior is. There are parts of where the animals come onto land in those regions to have their cubs, for example, and build their dens up on the shore. As the ice changes, though, it's not so much the fact that they've already got a land phase, it's the oceanic phase that's the problem. So it's not so much that they already come onto land, but as the ice retreats, the part of their life phase that deals with having to be at sea to hunt and feed is the part that's impacted. So for the life cycle of the bear that's on land already, they'll come on land, they'll be fine. Whether you're talking about Churchill or whether you're talking about somewhere in Siberia, that part will continue. It's the part that's at sea that's the component. And that's one of the most important things we talk about saying, I remember when I said the Arctic being ice-free. It's never going to be ice-free. The problem is at the time of year that it's important for the animals to be at sea, will there be ice for them to rest? So you have to separate out the seasons there. For the part of the time that they're on land, that's probably not going to change. Probably might be a little warm for them. But for the part that it's at sea, that's the primary issue. Other questions? Over here, you can get a microphone.
I'm coming up there.
Okay, gotcha. The difference between fat and blubber. Go home tonight, take some steak, take some bacon, fry it up, and the fat there will melt, as you know, and just then form this congealed mass when it cools back down again. The easiest way to think about blubber is to think about a loofah sponge that you then fill up with fat and lipid and oil, okay? So I can take a chunk of blubber here and put it here on the table and heat it up, and it stays there. It doesn't turn into this liquid pool and then just go out onto the frying pan. It stays there because it has structure. It has a matrix to it. It's like a protein sponge. And the animals will then just suck lipid and fat out of that as necessary and put it back in as necessary. So in fact, there's some very good evidence that even when the animals consume a great deal of their amount of blubber, their thickness of the blubber doesn't change very much because the protein structure still stays there. They just remove the fat out of it and then fill it back up again. So I can take a piece of blubber and have it sit there, and it acts like an organ. It's a material that has structure to it. I take a piece of fat, heat it up, and it just turns into liquid, and it's gone. That's the primary difference between the two, and the fact that for these animals, blubber, like I said, is important for fuel. They consume it during their migrations. They feed their pups with it. It's important for thermoregulation. It's important for water balance, as it turns out, for some other chemistry reasons, and for buoyancy. So much more than just fat. Plus, what happens in marine mammals is that blubber is all external to them. And so what you don't see is like great fat pads around the heart or the kidney or something like that that you would tend to see in humans or other terrestrial animals, because we just don't have the equivalent of blubber. There's just nothing like it for us.
All right. Anything
There's
else
one
out
more
there?
over here, Amy.
Okay.
I guess I'm up.
Over here.
Over here?
I just had a question on the graph that correlated CO2 concentrations
Okay. I see.
with
Yeah,
temperature.
Okay. Yeah.
How do you determine specifically the temperature?
Oh, it's really cool. It's very interesting. Ice traps gases in it, okay? And in fact, that was discovered by some of the people that used to work here by the university many, many years ago. And so what they can do is they can take an ice core, and by a variety of ways they can date it. And imagine what they can do is they can go down through here and actually extract the gases out of it and see what the CO2 was. Okay, that's fairly straightforward. You can imagine that. It also turns out that oxygen exists in a couple of different, what they call stable isotope forms. And those forms are dependent upon what temperature it is. So they can go in and extract the oxygen out of there too, measure the ratio of those isotope forms, and figure out what the temperature is. It's a brilliant way of doing this, and are able then to make those calculations backwards and show, based upon the oxygen, chemistry of oxygen, what the temperature was, and then directly on the concentration of CO2 in the ice itself. And the ice cores are fabulous, although I didn't show it here tonight. The deepest ice core they've got now is almost 2 kilometers deep, millions and millions of years old. It's fabulous to be able to go backwards in time. But that's how it's done. It's some very exquisite chemistry and very well recognized. Was there one over here? No? Change your mind? Okay.
Question?
Yeah.
Does the ice around the Antarctic fluctuate as much as the Arctic ice does, season to season?
Gotcha. What I didn't show you in that particular, what I didn't show you in that graphic is that just as in the north, the ice around the south expands and contracts. Now, it can't go all the way back to zero because there's a continent in the way, right? And the continent's the size of Canada and the United States put together, so it's pretty big. But on the outside, yes, the ice expands in the wintertime, contracts in the summertime, and what they're not seeing in the south is the same summer contraction, and the reason for that is easy to see. It contracts up to the shoreline. I mean, every year it contracts up to the shoreline. Wouldn't matter if it got hot or cold, the ice is going to contract to the shoreline. That's as far as it can get. What they are seeing now instead, though, is differences in the thickness of the ice on the continent, how fast it's flowing off, and just like in Greenland, how much of it's melting. So I didn't want to get into that tonight because of trying to explain how we measure those things. It's much easier to see just the ice in the Arctic. But in the south, its thickness, how fast it's coming off, and how much of it's melting. Because every summer, it will contract right back down to the coastline. You can't do the same cool graphics like you can in the north because it looks the same. A hot year, cold year comes back to the shoreline.
Yes.
Yeah.
You may have just answered my question, but
Okay.
when you showed that great graph about how the decrease,
Summer
the-
ice?
the ice, that was pretty much pertaining to the north.
That's correct.
Now, is there something similar like that that has been done pertaining to the South?
Yeah, like I said, it's hard to do that with the sea ice
Right.
because for the reason I talked about, it'll come up to the shoreline and that's it. There are other graphs that will show the thickness of the ice in the Antarctic at various locations, and also the temperature of the ice at various locations, and estimates of how much of that's coming off as fresh water. In Greenland, they can do the same thing, and what they've been able to show, and you've probably read, is the amount of fresh water coming off of Greenland is now exceeding expectations as that ice cap melts. What we didn't get into here tonight, because it wasn't the whole thing about climate change, is the predictions of how much that's impacting sea level per year. It's on the range of 2 to 3 millimeters per year right now in terms of sea level, which doesn't sound like a lot until you start multiplying it over 40 or 50 years and then start projecting it onto things like the Louisiana coastline, and now it starts to become fairly important. And if you melt out Greenland, for example, which would be hundreds, if not thousands of years from now, basically San Francisco, Central Valley of California, southern Louisiana, all those places are just gone. You melt out the western Antarctic ice sheet, and even into central California at that point becomes ocean. And it's a big issue.
Do you see that the Antarctic is moving?
All the continents drift, and so they, based upon the fact that the continents are all moving, yeah, they do. We have fossils from the Antarctic of dinosaurs and palm trees when it didn't used to be at the South Pole, when it used to be up near closer to India, and it's moved over in that time frame. That time frame is fundamentally different. That's in hundreds of millions of years versus what I showed you here, which was in millions of years, right?
That's amazing.
Yeah,
Thank you.
so in the millions of years time scale, insignificant movement relative to staying warm or cold. In the billion year time scale, then yes. So a billion years from now, when all the continents are somewhere else, we could, it's going to be a different
Tropical
story.
again.
Yeah.
Thank you.
Okay. Here.
I was kind of fascinated by that ice core data,
Yeah.
and I was curious about the convergence of the carbon or the oxygen isotopes and the CO2. If you've got a dozen ice cores from Greenland and the ice fields of Alaska and Antarctica and the glaciers down in Africa or something, but is there a remarkable convergence 100,000 years ago if you had a dozen ice cores that had that segment of the history? Would the oxygen isotopes be roughly the same at each of these places?
The way the Earth's atmosphere works is it is considered to be essentially one pool except for microclimates. And so like when I teach this part of Earth chemistry to my students, and I talk about how much CO2 there is when you go outside and breathe, the basic assumption is that the Earth's atmosphere is well mixed. So that for the purposes of CO2 concentration, for example, you can find local microclimates that are different, but on average, assuming on these large ice sheets where you're not going to have a microclimate, what you're going to see in the Antarctic is what you're going to see in the Arctic. The difference comes into the time scale. The Antarctic is very, very old ice. So we can go down 2 kilometers and several million years there. In Africa and in other places around, like you said, other places in Alaska, for example, where you get that, you can't get that time resolution. So you've got to think about, a million years worth of ice here in the Antarctic and what that pattern looks like, and maybe, 60, 70, 100,000 years in other places and what it looks like. So you can match up this part, but you can't match the whole thing because there's nowhere else that you're going to get that except for some of the deep, deep Greenland cores that are going to be that old. So yes, they match, but you've got some here that are sort of only this thick and some that are this thick. And so you can't do that across the board, except to say that across the whole planet, the atmosphere works very well. Most of the CO2 data that match this, for example, that I showed you, the one graph that expanded the last 150 years, what I didn't point out to you was that there on the left was taken from the ice cores, and the part that continued up over here, that continued on in that same line, was taken from gas samples collected near Hawaii on Mauna Loa in a very famous set of experiments done by some people out of Scripps in San Diego. So they connect right up with one another. There's no major mismatch. And I've never heard of that being a problem, that something from Iceland is different than something from Greenland, than something from the Antarctic. As far as I know, they match up very well, primarily because the Earth mixes its atmosphere very well. And you know, the temperature changes we're talking about are subtle. The difference between the Little Ice Age in Europe in the 1400s and the normal temperatures on the Earth average temperature was only like 2 degrees. So you've also got to go away from here answering people who say, oh, who cares if it warms up, you know, 1 degree. Last week was minus 60, today it's positive 40. That's 100 degrees difference. What difference does that make? The difference is you're talking now about the average temperature for the whole planet. And the difference is separated the Little Ice Age from normal temperatures in Europe, kicked the Vikings out of Greenland, the whole thing was only about 2 degrees. And so the significance of just a little bit of temperature change on average across the whole planet has massive changes in terms of the balance of the planet. And that's the important part, not the fact that it's 60 degrees warmer today than it was last week. That's noise on the system.
I got a question for you, right here.
Gotcha, okay.
I wasn't really sure how to word it, but is there really a difference between adaptation, which is what you're talking about right now,
Yes.
climate and animals, and evolution? And
Sure.
are we not just merely observers of this stage of evolution and maybe educated observers that weren't here many, many years ago?
Absolutely. The concept when we teach the difference between adaptation and evolution is evolution is the process by which you get speciation, by which the fact that there are seals in the north of some species and seal in the south of other species, that all the different animals are all who and what they are. It's the process involved in it. But the process of how you live in your world is the adaptation. Now, some of that's fast and is built into the genetic capabilities of animals. We're really poor, for example, without all our wonderful coats and everything, of being able to live in the north and the south, the extreme north and the south. It's because we can wear wonderful clothes that we could live here. Imagining try to live here last week if all you had was just a pair of underwear. It's not going to happen, right? And so the animals that are adapted to live on the ice have done so during the process of evolution, which is a very slow process. But the adaptations are very specific. So there are things like claws for moving around in the ice. Some of them even have different structures in the joint of the elbow, so they can pull themselves along in the ice differently than their cousins in the south or cousins in more temperate regions. There are all these specific adaptations that are the result of evolution. And yes, we watch that, and nobody's making an argument that we're changing the evolutionary history of these animals, because the time frames are just totally different between how evolution occurs and how the changes that we're putting on the system occurs now. It's two different time frames. But it's important to realize that one is the process, essentially the other is the result. They're not essentially the same thing. And these animals are exquisitely adapted to be in the water. They're exquisite, the ones we talked about tonight, exquisitely adapted to be on the ice, and wouldn't do well if you put them somewhere else, for example, because they've adapted to that over evolutionary time. So it's a time scale difference and a process difference. Yeah.
Are you familiar with the magnetic field and how the theories of how it's changed from pole to pole?
Oh yes,
and
absolutely.
if so,
yeah.
what effect does that have on the climate?
I'm going to have to rely on a couple of my geology friends in here to tell me the time scale of the magnetic pole changes, because I don't remember them off the top of my head. But I would imagine they have a significant impact on a variety of different systems and could very well be built in to some of those long-term changes I talked about. Somebody one of my geology friends want to jump in here? Yeah, Roger? 1,000 years, okay. So in the time scale of 1,000 years, I would guess then you could have magnetic changes. Whether that impacts ocean currents or stuff, I don't know. I'd have to rely on some of my oceanographer friends to tell me that. But I've never seen anything that actually talks about magnetic implications and how that would impact temperature or ice. It's going to cause some problems for the animals that navigate magnetically, of course, but how that would impact some of the issues that we're talking about tonight, I don't know. I'd have to rely on a couple of the other experts here in the audience to answer that question for me.
We have one way
Probably
in the back
do
here.
afterwards, yeah.
Oh, sorry. We have one in the back here.
Okay.
On the one graph, you showed temperature and CO2 overlaid.
Yep.
Then when you zoomed in to recent years with CO2,
Right.
you didn't overlay temperature, did you?
No, I did not. And the reason... Okay, go ahead.
Yeah, go ahead and explain that.
Yeah,
or-
the reason why is because the temperature hasn't caught up or is lagging significantly behind the CO2. The CO2 is now spiking so fast that it's out of the same time sequence that what we talked about there. And so while we have 10,000 years up and 90,000 down, that I sort of showed you how those two related. Now we're at the 10,000 peak, and we're getting ready for a 90,000 down if the Earth works the same way, but now we've blown CO2 off the graph. And so now the question is, how are the two of them going to relate to one another? So I didn't plot it there because, first of all, the scale's way different than what we'd seen before. But secondly, because that's the problem now. We're watching temperatures start to come up, but it's lagging seriously behind this. It's not tracking exactly along. If it tracked exactly along, we'd be in a world of hurt right now with that much of a temperature, that much of a CO2 trace. That's where the modelers come in. That's where the people that are really good at this and are attempting to try to figure out how are we going to predict the temperature is going to follow along with the CO2, or is it going to follow along? The best data at this point shows that we're warming up. Maybe that'll separate in the future. I don't know. We need people to understand how those two things are related to one another in the current situation. We can go backwards in time quite readily. The question is, how do we project into the future? That's the trick. That is the true trick to this.
Has the temperature of Antarctic gone higher than what you showed on the one graph?
The temperature in the Antarctic, those again are average ice core temperatures that I showed you. And so, yes, there are parts of the Antarctic that are getting warmer, but that's not what we would track there. Again, you've got to look at ice core temperatures, not sort of like daily weather temperatures for that.
I don't see any more
Done?
hands.
We done? All done for the night?
I think you're done.
All righty, thank you. And I'll talk to you up here too if you want to. Thank you very much.